In the next model, a neural network was made. Some libraries were imported. The first was load.txt, which took the data from the table and put it into a string. Next, sequential is imported and is the first layer in the neural network. This is because it specifies the fact that we are going to create a model sequentially, and the output of each layer will be the input of the next. There are many hidden layers that can be used in a neural network, like dense, convolutional, and pooling. However, since pooling and convolutional are used for image processing, only dense was used in this case. Dense layers do a linear operation for each value in the feature. The linear equation is dependent on how valuable the feature is in the prediction. Next, the dataset was loaded and transferred into an array. Once again, the X and Y dataset were split into an input and output values, just like in the logistic regression model. Further, the neural network was defined. The model was activated with the sequential function, as it told it what layers would be added to form a model. Nevertheless, 2 dense layers were also added. The first one had 12 nodes in its hidden layer with a ReLU activation. As I said before, the dense layer adds a linear operation to the input. The activation tells the neural network what program to use, in this case, a ReLU function. The second layer was also a dense layer, but this time it was with a sigmoid equation. This picture of a neural network shows us how a neural network exactly works like in depth, letting us have a better grasp on these activation functions. It starts out with initial nodes that are weighed separately, depending on their influence on the neural network. The weights then go to a node where the loss and bias is calculated. Then, the output is put through an activation function to reduce this bias, and this is where the different activation functions such as sigmoid, tan, and ReLU come into play. The output from these series of events is what gets sent to the next node, where the same is repeated. Now, the model was compiled with a variety of other parameters. Some were the loss function and the atom optimizer. The binary cross entropy tells the user how accurate the program is by showing how close the output value is to the predicted value. The atom optimizer adapts the model to make it more accurate by fitting it to the true output value. After applying all these parameters, the model was actually run to fit the X and Y values. The epoch value was 200, meaning that the dataset was run through the model 200 times. Further, the accuracy was then stored in a variable called predictions. The final line of code allows the expected value and the predicted value to be printed out for the first 5 cases. Down below, you can see exactly how accurate each epoch is as it increased with accuracy. The first epoch starts at about 84.79% and then goes down to reach about 85%. Nevertheless, you can see how accurate it is, as the predicted and expected values of the first 5 samples are shown. In conclusion, the programs explained can be an accurate, efficient, and accessible diagnosis for cardiovascular disease, a condition that kills thousands of people every year. Also, the fact of the matter is that diagnosis can lead to early treatment, reducing the amount of deaths every year, as strokes and heart attacks can be stopped early on. Nevertheless, this project can be grown as the algorithm can be added to an app. The app can also be programmed to find one's blood glucose levels, cholesterol, and blood pressure, which can be added into the algorithm to see if the user has cardiovascular disease. Using an effective app can be one of the most accessible and efficient ways of diagnosing cardiovascular disease, the leading cause of death in the United States. Thank you for listening, and I hope you have learned a little more about cardiovascular disease and machine learning.